Hi there! In this video I'm taking a closer look at the UM25C USB tester to see how it compares to the UM34C and an interesting fake tester, the so-called UT25, which costs just half the price of a UM25. As with the UM34C, the UM25C comes in a nice metal box to keep it safe, but makes it hard to get out initially until the padding kind of wears in a little. In case you're wondering about the C part of the names, this letter refers to communication and means that the C variant has an additional Bluetooth port to allow measuring from an app and also record data in spreadsheet format. Apart from the Bluetooth port, which can be turned on or off, the C and non-C variants are identical. Here we have all three in a row: the blue UM25C, the red UT25 and the yellow UM34C. Plugging them in, you can see that the UM25C and its clone show 5 digits for voltage and current, while the UM34C uses 4. This translates to 1 mV and 0.1 mA resolution for the first two, and only 10 mV and 1 mA resolution for the UM34C. The reason that the current values are different is that the UM25C shows the sum of the current consumed by the UT25 and the UM34C together, the UT25 only the current used by the UM34C, and the UM34C of course 0 because nothing is plugged into it. This is a nice illustration that all USB meters are hiding their own power consumption needed for running the display and processor. They only display the current flowing out of them, not what goes into the meter. Because of the power consumed by each meter, we also have a slight voltage drop across the series, which of course gets larger the more current we draw. The startup screens of the three meters look very similar. I paused the video to have more time to compare. It is clear that the no-name guys producing the fake UM25 sneakily replaced Ruideng's company name with the word welcome and UM25 with UT25, which can be very easily done with a hex editor in a binary copy of the firmware, as the words have the same number of characters. The menus are identical between all three devices, and since I already went through the menus and how to use them when I reviewed the UM34C, I won't do it again. If you have not seen it, I put a link to that video in the description below. Here's just a quick run through. Starting with the already familiar main menu and pressing next on each of the three devices. The menu displaying the charge mode an external device may be using. Since no charger or battery is connected at the moment, the mode is unknown. The capacity and energy measurement menu. The menu to measure cable resistance in 2 steps. The graphical display of voltage and current over time. And finally, the display setup. And back to main. It is clear that the clone uses exactly the same firmware as the genuine devices, and RDTech, the Ruideng company, when I contacted them about it, confirmed that the UT25 you see here is a cheap fake of the UM25, and expressed their concern that its quality and calibration will probably not be to the level of care RDTech uses for its genuine products. What are the specs of the real UM25? This is an extract of the datasheet. The most interesting values are here: voltage and current range, and on the other side resolution, and below that the accuracy. It is interesting that RDTech used the rarely used promille designation instead of the much more familiar %. This might turn out to be a bad move because most people may easily misread 0.5 promille with 0.5% when it's really 0.05%, which is of course 10 times better. Same on the current accuracy with 1 per mil, which really means 0.1%. The other possibility is of course that this was supposed to be 0.5% and 1%, and promille designation in the spec is a typo. Let's see if we can find out. What do these accuracies mean in practice? 10 volts measured with 0.05% accuracy means an error of plus minus 5 millivolts, or the measurement could be anywhere between 9.995 and 10.005 volts. But then the additional 2-digit error comes in, and we have to assume the worst case. It adds 2 digits on the high value and subtracts 2 on the low one. This means a true 10 volt could be anywhere between 9.993 and 10.007 volts and just be in spec. A similar calculation for the current on the right here shows that 1 amp could be shown as 0.9986 to 1.0014 amps and still be in spec. These are worst case calculations. In reality, the testers are usually better than their guaranteed minimum specs, and the plus minus 2 or 4 digits may actually cancel part of the error instead of adding to it. So I would be disappointed if a true 10 volt voltage wouldn't be shown as 10.000, or maybe with just 1 digit off on either side. Okay, so why not simply verify the accuracy using a reference voltage source like this one? It should produce precisely 10.00096 volts, and even the venerable Solartron multimeter agrees within 60 microvolts or so. The answer is that reference voltage sources are designed to test high impedance multimeters drawing basically no current, and not to power USB testers, microprocessors and LCD displays. Let's have a closer look at the UM25C. It is built exactly like the UM34C in an open sandwich, where the central PCB has the LCD and USB-A front and end connectors on one side and all the other components on the other side. A top and bottom plate protects the PCB, but the sides are open for airflow and to access the micro USB and USB-C connectors, as well as 4 buttons, 2 on each side. For the C variant, a second PCB with the Bluetooth chips are added to the bottom plate, which has an additional on-off switch. Since all the components except the LCD are on the underside of the PCB, it is sufficient to only remove the 4 screws holding the rear plate to examine the PCB and the Bluetooth board. The Bluetooth board connects to pads on the main PCB with 4 springy contacts. There are not that many components on the board apart from the big USB connectors. Key is of course the microcontroller, which is an ST Microelectronics 8S005C6. If that sounds familiar, it is because the UM34C uses exactly the same chip. The same is true for the voltage regulator 5333B, sitting between the controller and the big silvery electrolyte capacitor. The regulator is a low dropout type for 3.3 volts. Where the UM25C differs from the UM34C are these 2 devices here. The smaller one on top is marked as A810, and I think it's an electronic single-pole double-throw switch. That chip's not on the UM34C. The second one is marked CAQD, and I have not managed to find any datasheet for it. I guess it's an op-amp of sorts, similar to the one in the UM34C. I think that both of these are for current measurement, because for 1 milliamp resolution the voltage drop across the current sense resistor changes by just 10 microvolts. The voltage drop is probably amplified by the op-amp, and the other chip could be used to change the gain and thereby implementing 2 ranges. Lastly, we have the current sense resistor, which is a precision 10 milliohm type, and the 4 big contact pads where the Bluetooth board connects. They are marked RXD, TXD, ground and VCC, as you would expect. 4 smaller pads are marked VGRS and probably for programming debugging. Moving to the Bluetooth board, you can see the antenna, a PCB traced to the left of the DXBT18 chip. There's another one of those tiny A810 chips and another voltage regulator next to the on-off switch. If you look at the ADC in the datasheet, it gets its reference from the VDDA pin. And since there is no alternative reference voltage on the board, this pin is directly connected to the 3.3 volt supply rail, which I confirmed by measuring the voltage on the VDDA pin. Some versions of this controller have separate VREF pins that allow cool tricks to improve resolution by analog zooming, but the version used in both the UM25 and UM34 does not have these pins. Also, there is no programmable gain for any of the 10 ADC channels, so all channels basically measure voltage from VSSA to VDDA, which in this case is from 0 to 3.3 volts. The ADC itself has only 10-bit resolution, and that's definitely not good enough to meet the resolution and accuracy specs of the UM25C or the UM34C for that matter. 24 volts divided by 1024 is 23 millivolts per bit, a long way from displaying values with 1 millivolt resolution and measuring at 0.5 millivolts. Similar, 5 amps divided by 1024 is 4.8 milliamps, which is clearly not fine-grained enough to display 0.1 milliamp values. The solution lies in applying mathematics and oversampling to gain additional ADC bits. This is possible because the ADC is very fast and takes just 14 clock cycles for a conversion. If the software collects 4096 samples from a channel and then averages the result, it gains 6 extra bits. Basically trading conversion speed, that is how many measurements are displayed per second, for more resolution. With 16 bits, the effective resolution becomes 0.36 millivolts for voltage and 0.08 milliamps for current, which would be good enough for meeting the specs. This is of course all speculation from my side, but something like that is very probable. This is how I think the measurement circuitry in the UM25 along with similar devices looks like. The standard USB 4 wires are coming in from the left and leave on the right. Input and output are basically connected through, except for the ground, which is going through the current sense resistor. The reason why sensing happens on the ground or not on VBus is because it allows a shared common ground for all analog measurements, which is important since all are going to be measured by the same ADC and thus share the same ground connection. 3 resistor voltage dividers scale the voltage on the VBus D- and D+ lines down to the 3.3 volt range the ADC uses. An amplifier is needed to boost the voltage drop across the shunt resistor because even at 5 amps the voltage drop is just 50 millivolts, and that isn't nearly enough to allow reasonable accurate measurements by a 3.3 volts ADC. A PTC or a similar device provides a way to measure temperature. This temperature sensor is close to the voltage regulator, and since that regulator is a linear type, it converts anything above 3.3 volts into heat. That means it gets rather hot, even more so at voltages above 10 volts or when the display is on and at high brightness. Since the regulator is also providing the reference voltage for the ADC and will have some temperature drift, it is possible that the real reason for measuring and displaying temperature is to allow the firmware to correct the ADC readings for temperature drift of the reference voltage. The voltage measurements on the D- and D+ lines are for compatibility with very old USB chargers and devices which used resistors to establish certain voltage levels on D+ and D- to signal what charge current they could handle. In total, I think the circuit uses just 5 of the 10 possible analog channels. The high-res oversampling trick is really only needed for 2, VBus and the current. The rest can be handled with a standard 10 bits resolution. Before we get into measurements, let's have a quick look at the fake. This is where it came from. In case you are rushing to buy it, no, it's currently no longer sold. Whether that is because they are out of stock or for some other reason, I don't know. Cunningly, it's called UT25, it is red instead of blue, and they replaced the tapered front end for a real UM meter with a straight end. Not sure if that was done to avoid legal issues, because clearly the circuitry and the firmware has been copied straight from Ruideng. At the time I got it, the price was half that of a real UM25. Unsurprisingly, it did not come in a swanky metal box, but rather a flimsy plastic bag. It is constructed in exactly the same sandwich format as the UM25 or the UM34. Same connectivity and buttons, and even has apparently provision for a Bluetooth board. It opens the same way too, and at first glance the boards look pretty similar. It has exactly the same ST microcontroller chip on board. Well, they kind of had to, otherwise the copied firmware won't work. The other two chips have different numbers. I found the 3157 on top, and I think it's the same electronic switch chip used in the UM25. I threw again a blank looking for the other one labeled CASP. If you recall, the UM25 chip was called CAQD. But besides all that, what is this? A hair? And look at the soldering work, especially that blob covering at least one adjacent track. Looks like saved only by the thin layer of solder mask from a short circuit. The full horrors of botched hand soldering, and look at all the spluttered solder blobs just waiting to dislodge and cause short circuits. Bear with me while I'm trying to remove that hair or whatever it is. In the meantime, enjoy the views of high quality soldering. Where did it go? Oh, there it is. Would you just look at the blobs of solder? The other end of the board is not any better. Look at the spluttered solder all over the place. This can come loose at any moment and short things. They have to go. This is just a bit of the cleanup I did. I won't bore you with the rest. But for now I haven't reworked the soldering itself. It works in the moment, and I'm kind of curious to see for how long. At closer examination, the PCB, tracks and component placements are very similar, but not quite identical. Here's the fake UT25 board. Keep an eye on this area here and the 6 programming pads. And here's the real UM25 PCB. You notice the difference are the programming pads, 6 for the fake and 4 for the real one, and something like 4 additional resistors and 2 capacitors, where the UM25 has just empty space. Finally, here's the UM34 board for comparison. It is quite similar. Clearly, the only difference I could make out between the UM25 and UM34 is one additional USB socket, the additional switch chip, and a different op amp in this area here. A side-by-side view of the key differences. In the middle you can clearly see the additional components used by the fake, which could well be related to the programming debugging interface and the 6 pads rather than the 4 of the real device here on the left. I included the pictures of the current sense resistors for all 3 devices because the UM25 resistor looks quite different. It could be that the UM25 uses a higher precision device, while the fake and the UM34 uses standard resistors that look quite similar. With all the boards looking so similar, I wondered if I could create a Franken UT25C version out of the UT25 by combining it with, for example, a UM34C's Bluetooth board. It turns out you can't. If you put the empty top board of the UT25 on top of a UM34C Bluetooth board, you see that the mounting holes don't fit. The rear holes are the same, but the position of the holes at the UM34C's tapered front end are different from the ones in the square UT25. And also the cutout for the large capacitor on the main board is slightly offset. Okay, just one more thing I'd like to explain about error graphs, and rather than explaining it again and again for each graph, I thought I'd do it just once, and here it is. The tables and graph here are pure math and not based on any measurement values and not different for currents or volts. They only depend on the resolution of the display. Since the UM25 uses two different resolutions for volts and current, I made two tables, and for convenience I use volts and amps as example values. The tables show that for any multimeter presenting values with 1 millivolt resolution, the significance of changing the most right digit, that is the 1 millivolt digit, by 1 depends a lot on the absolute voltage being measured. While at 24 volts, a one-digit error, say 24.001 instead of 24, is just 0.004%. The same error at 4 volts, 4.001 instead of 4, is already 0.025%. For a current display using 0.1 milliamp resolution, the differences are even more noticeable. At 5 amps, a one-digit error is just 0.02%. But at 10 milliamps, the same digit means 1% error. This, by the way, is the reason why multimeters switch range to always use a range that shows the largest value. No decent multimeter would show 10 milliamps in a 5 amp range. But so far USB testers seem to have just one range for current and volts, so the effect is noticeable and also causes error plots to become more and more jagged and jumpy the lower the measured values get. To measure the accuracy and resolution of the volts readout of the UM25C, I'm using this setup. The power supply is remotely controlled to create test voltages from 4 to 24 volts in tiny steps. The test voltage is fed into the UM25C and the 3441A 6.5 digit multimeter for comparison. The multimeter measurements are remotely obtained. In previous videos I have built the power supply and the remote control program, and if you haven't seen it, I add links into the description. This is the program driving the measurements. The only new thing is the serial SCPI command add-on, which is just a handful of Python lines to send standard commands for programmable instruments, or SCPI, text strings over a serial port. With that addition, I can now control many additional instruments, an Agilent 3441A being one. One of these days I will probably make another video about the multimeter and SCPI, but for now let's just take both as given. To look at resolution as well as accuracy, the first part, from 4 to 5 volts, increments the voltage in tiny 20 millivolt steps. That's 50 measurements just for that. At each step we take a picture and a high resolution measurement using the 10 volt range, which offers the best resolution. Once 5 volt has been reached, I switch to faster increments of 100 millivolts for the rest of the measurements. However, I'm using manual ranging at the multimeter, so I need to program this in two parts, 5 to 10 volts and 10 to 24 volts, to allow me to change the range. After pointing the webcam to the UM25 and starting the program, you can do other things. Once the program is finished, you end up with a folder of image files with a sequential number and a CSV file containing the power supply settings and the measurements from the multimeter. All that is now needed is to open a spreadsheet and manually add the readings from the UM25 based on the webcam images. Because the sequential numbers are in the spreadsheet as well, it's very easy to find which image corresponds to which step in the program. You may wonder why I did not use the Bluetooth recording capability of the UM25, and the truth is I'd love to, but I haven't found an easy way to synchronize the UM25 recordings with this spreadsheet. The UM25 records about once every second, and so you get many readings for each step of the program. It is not easy to come up with a good way to reduce the thousands of readings into the 240 ones that match the moment the multimeter was capturing the same data. And you can't design a filter algorithm that presumes that the UM25 is behaving correctly to filter the data and then use it to verify that it behaves correctly. In the end, Once you get the hang of it, the picture method works quite fast, and it has the advantage that we can use the same method for the fake USB tester that has no Bluetooth. Here's the result for the UM25C. The UM25C and the multimeter track so closely that the two lines are on top of each other. You can see that the error is on average just 0.01% and at worst stays within plus minus 0.03%. So yes, the UM25C meets and slightly exceeds the voltage specs, especially so if you remember the discussion about the problems of the error plots at low values. Before we embark on verifying the current accuracy, I like to use these simplified schematics to explain why I'm doing things in a certain way, which may be hard to see in the video footage. Normally driving a selectable current through a measurement device would be easy. Set up the power supply to constant current instead of constant voltage and wire it up like here. The current flows into the UM25 and out through the multimeter set to current mode. Unfortunately, this doesn't work for USB testers because they need a minimum input voltage of 4 volt, in this case for the microcontroller and the display to work. Because the multimeter acts like a dead short, the voltage at the input immediately collapses to a few millivolts, precisely the voltage to drive the selected current through the combined but very low internal resistance of the UM25 and the multimeter. The easy fix is to increase the resistance on the load size, in this case, for example, 10 ohms. But this comes at a price. The first limitation is the minimum current we can measure, which is around 0.4 amps, because anything less won't drop enough voltage at the 10 ohm to power the microcontroller. The second is the maximum current, which is reached when the voltage drop reaches the maximum allowed input voltage of 24 volts. For 10 ohms, that's around 2.4 amps. Also note, at this stage, the 10 ohm resistor needs to dissipate almost 60 watts, so clearly only power resistors on heat sinks, possibly fan-cooled, can be used. Lowering the resistor value moves both the minimum and maximum current upwards, but it increases the stress on the resistor even further. In the end, I settled on the 10 ohm as a compromise and the current range of about 0.4 to 2.3 amps. This includes the most commonly used USB charge currents where good accuracy would be most useful. To cover the really low currents, I decided to do a second run using a 60 ohm load, covering the range from about 70 milliamps to 0.4 amps. One thinks it should be possible to use the circuit in constant current mode and use the PC to step through the selected currents, but surprisingly it turns out that this does not work at all. It took me a while to figure out why, and I thought it might be worth sharing. The reason why constant current won't work is that the current the power supply sees isn't anything but constant. It is a steady load current B plus the current used by the UM25 itself, A, and unfortunately that current A is fluctuating a lot depending on what processor and Bluetooth chip do. The power supply tries to keep the current it supplies constant by varying its output voltage to compensate, but because the voltage to the USB tester fluctuates now, the current in the load circuit does as well. By forcing the A current to be constant, we have transferred the fluctuations into the B current instead. In this experiment, the power supply is providing 100 mA constant current, and the Solartron on top is showing the voltage and the 34401A below the current through the load of 60 ohms. You can see that the voltage and the load current fluctuate like mad, while the UM25, with its slow update rate caused by all the oversampling and averaging, is rather immune to these fast changes. The problem is that taking a reading with a multimeter and a picture of the UM25 displays are two different steps and not happening exactly at the same time, so both devices will register different current values, making any attempt at precision testing hopeless. Changing to constant voltage confines the current fluctuations to where they originated, namely the connection between the power supply and the input of the UM25. The constant supply voltage means that the voltage at the output of the UM25 is now steady too, and that means the load current is steady enough to allow the measurements to go ahead. Constant voltage mode means, of course, target current selection can only be done indirectly using Ohm's law with the selected voltage and the fixed load resistor value. But that's fine, since for this test the absolute load current value do not matter as long as they are reasonably constant during the time both UM25 and the multimeter take their measurements. Okay, one last schematic, I promise, and that's a very easy one. With the setup shown earlier, we can verify current accuracy from 70 milliamps to 2.4 amps in 2 runs. But what about the full 5 amps? The limits of my lab equipment means we can't use automation any longer and we have to use a manually operated electronic load instead. The slight complication is that both my 6.5-digit multimeters can't measure these high currents directly. So for the full range test, I'm going back to the external sense resistor method used in some of my previous videos. This is a precision resistor, and all I have to do is use the multimeter to measure the voltage drop across it, which I then convert to current using Ohm's law. Let's start with the automated method. There is a bit of voltage drop to the UM25, and the 10 ohm resistor plus its wires is a bit more than 10 ohms. Oh, and by the way, I put it up there next to the scope with a fan on top for cooling. This is the program driving the measurements. In hindsight, the 50 millivolts was a bit of an overkill, resulting in almost 400 steps and taking 1 hour and 22 minutes to execute. Since the UM25 displays current with 0.1 milliamp resolution, I wanted to be sure it did the right thing. This is the result for the range from about 0.4 amps to 2.3 amps. Again, the multimeter and UM25C are so close that the lines are on top of each other. The current measurement error was 0.01% on average and stays within plus minus 0.03%. This is well within the specification, but we have not looked at the other ranges yet. Using exactly the same method and program, but with a 60 ohm resistor, I measured the error for the lower current range. The multimeter and the UM25C plots are still inseparable. As explained before, at these lower values the errors start to become larger and the line becomes more jagged, but overall the error is still within spec. For measuring the full range current, I'm using the electronic load you see here on the top left to select the target current. The current is verified using an external sense resistor you see on the right next to the UM25. The voltage drop is shown on the multimeter. I'm showing this in a time lapse to speed things up. Note that since we already tested and checked the lower currents, I'm only measuring a few of the lower currents before doing 100 milliamp increments all the way to 5 amps. As you can see, the UM25C behaved very well. The error stays within plus minus 0.02%, well within the plus minus 0.1% specification by a large margin, which is an excellent result. I want to point out that while the external current sense resistor itself has only 0.1% tolerance, I did a control measurement at lower currents alternating between the method of the external current sense resistor and the bench multimeter in current mode to establish the true value of the external sense resistor, which I then used for the rest of the conversions. I'm sure you are interested how the fake tester accuracy compares with the genuine one. To find out, I ran the fake tester labeled UT25 in this diagram through the same tests, and for good measure I added the genuine UM34C into the mix as well. Here are the results for the voltage accuracy test. Both the UM25C, the blue trace, and the UT25, the red trace, are clearly miles better than the UM34C, but to be fair, that's mostly because of the limited resolution of the UM34, especially towards the lower voltages. If you look carefully, it does appear as if the red trace of the fake is slightly closer to the 0% error than the UM25C. Removing the UM34C from the plot allows us to zoom in, and the greater detail confirms that the red track of the fake UT25 is actually a little closer to 0% than the UM25C. We are talking tiny amounts here, 0.01% or so, but it's still somewhat surprising. Is the fake really better than the original? Looking at the lower part of the current measurement range of 70 milliamps to 2.3 amps shows a slightly different picture. Okay, the yellow UM34C appears to have trouble at low currents, but as I explained, that's caused by the limited resolution, blowing single-digit errors out of proportion. At higher currents, it holds itself very well to the UM25C. The trace shows a little bit more zigzagging, which is again a resolution issue, not one of accuracy. The red trace of the fake UT25C is quite a bit worse than the UM25C and even the UM34C. There's an interesting step, which is right where the first run of tests from 0.07 amps to 0.4 amps ended and the run from 0.4 to 2.4 amps starts. You can see that the curve starts at roughly the same level and then drops, reaching the 0.4 amp, and then recovers and slowly starts dropping again on the way to 2.4 amps. If you recall from the schematic diagrams, the current for these tests is determined by the voltage setting, and in both runs the endpoints are where 24 volts is applied. One time to get 0.4 amps and the other time to get 2.4 amps. 24 volts for a 3.3 voltage regulator means a lot of heat. Don't forget, the regulator is also acting as a reference for the ADC, and so I started to suspect there might be a temperature drift problem in the fake tester. We'll get to this in a moment. First, let's look at the accuracy for high currents, and as you can see, the story continues. We know already that the blue UM25C is extremely accurate and stays so for the whole range. On average, the UM34C is equally accurate but zigzags quite a bit around the 0% line. However, it stays within 0.1%, and that's well within spec and a very good result. Also, the UM34C tops out at 4 amps and can't measure any higher currents. Not so good for the red trace of the fake UT25, which starts at 0.1% and then drops to 0.2%. And that would be out of the plus minus 0.1 spec for the UM25C. Now to temperature drift. I don't bore you with video footage of the test because it's even less exciting than the other tests. Basically, I made sure that all three testers were at ambient room temperature and then applied constant voltage of 22 volts and a load of 33 milliamps to each. I kept these conditions and noted every 10 seconds the temperature and the reading of voltage and current. I choose 33 milliamps because I had a power resistor of 660 ohm at hand, but more importantly, I wanted a fairly low current, because low currents cause only the tiniest voltage drop at the internal current sense resistors and are therefore the hardest to measure accurately. In each of the three graphs, the red curve is the temperature readout of the tester with a scale on the left y-axis. The blue line is the voltage error and the yellow line is the current error, both using the right y-axis. For the UM25C, the voltage error is only changing minutely, but there seems to be a large step in the current error. This step represents the change of the least significant digit, changing the error to 0.5%. Compare this with the UT25 on the right. The voltage error isn't too bad, but the current error shows a massive change. The whole change of the UM25C of 0.5% fits into just one of the horizontal lines on the UT25 graph. The UT25's current error increases 5 times as much to 2.5%, confirming there is a temperature drift problem, probably buried in some low-spec components used in the fake tester circuitry. The UM34C voltage error is quite okay, and at the very low currents used here, it suffers from its lower resolution, causing a fluctuating single digit to register as a jump of 3%. Only a few more things to look at. The first, how low can the voltage drop before the UM25C shuts down, because its regulator can't produce the 3.3 volts. To test this, I started at 5 volts and gradually reduced the voltage. It is not just important to see if the UM25C still works, but also if the value shown is still correct. After all, the chip may still work if its supply drops to 2.5 volts, but the reference voltage for the ADC has to remain at 3.3 volts or the measurements will be all wrong. It shuts down below 3.862 volts, and up to this point the voltage shown was correct. While the UM25 shut down after the voltage fell below 3.862 volts, that doesn't mean it will spring back to life when we go above 3.862 volts. Most testers need a substantially higher voltage to boot than the lowest value they can measure once they are running. Here I'm increasing the voltage slowly to see when the tester will wake up. 4.148 volts and still nothing. 4.2 volts and we're back running. I did these tests only for the UM25C, but casual observation tells me that the UT25 behaves the same way. Another test I only did for the UM25C is to measure the consumption of the tester with and without Bluetooth at different display brightness levels and with the display off. If we just look at the averages, which is probably the most useful value, we see we have quite a variation. Just below 10 milliamps with no Bluetooth and display to just about 32 milliamps with Bluetooth and full brightness. You may wonder, why should you care about what the tester uses? Let's say you want to know what the capacity of a fully charged USB power bank is. You would discharge it over a few hours through the USB tester into some load, which could be just a fan, torchlight or similar. The USB tester records capacity and energy until the power bank is empty and shuts down. The problem is that what you see on the USB tester as capacity is only based on the current through your load. The battery, however, was discharged by your load current plus the current used by the USB tester itself. The lower your load current is, the more significant is this error. For example, if discharged at 300 milliamps through an UM25 at full brightness with Bluetooth enabled, it adds its own 30 milliamps, 10% more on top, so the battery is drained with 330 milliamps. After 10 hours, the UM25C reports a capacity of 3000 milliamp hours based on the 300 milliamps it showed on the display and 10 hours elapsed, but the battery really delivered 3300 milliamp hours. That is, the true capacity is 10% more. Now, this is not a problem of the UM25C alone. All USB testers have this problem. This is why you need to know the consumption and in particular how to minimize it if it gets in the way, as in measuring battery capacity. So in this case, I would turn Bluetooth and the display off and increase the load to say 1 amp. With that, the 10 milliamp consumption of the tester is just 1% extra, which is an error that is usually tolerable. What then is the conclusion? The UM25C definitely meets its spec and is an improvement in both resolution and accuracy over the UM34C. There is no difference in functionality, which is exactly the same for both. The so-called UT25 fake is a strange beast. It measures voltages even more accurately than the real thing, the UM25C, but its accuracy on current is quite a bit worse and out of the UM25C spec at higher values. The shoddy soldering quality is a real concern to me, as it is large drift at higher temperatures, pointing to substandard components. The fact that my unit worked as advertised seems more like a fortunate accident, and how long it will withstand the stresses of being used remains to be seen. One could argue that this is a risk worth taking if, like here, the fake is a lot less expensive, so if it dies prematurely, it isn't the end of the world. But then, can you really trust any of its readings? And if a loose solder blob finally causes a short and blows it up, who knows what it does to your tablet or smartphone to which it was connected at the time. A real UM25 or UM25C is definitely recommended if you are on the lookout for a good USB tester. If you don't need 5 amps and don't need millivolts and 0.1 milliamp readouts, the UM34 or UM34C is still a good deal. Fake testers like the so-called UT25 are best avoided. Thanks for watching.